Hello everyone, welcome to ELO YouTube channel where we discuss organic chemistry in simplified terms. We will be discussing in details factors affecting proton NMR chemical shift. Before we proceed to discussing factors affecting proton NMR chemical shift, let's first of all define what proton NMR chemical shift is. The proton NMR chemical shift is a chemical shift that ranges from 0 to 12 parts per million. At the 0 point, we use the trimethylsilane as the reference point, which has a chemical shift of 0. Important thing we have to note here is shift from 0 towards 12 is known as downfield shift or the shielded effect. While shift from 12 towards 0 is called the upfield shift or the shielded effect. One of the factors that affects the proton NMR chemical shift is the distance from the electronegative atom, or what we call the inductive effect. The closer the hydrogen to electronegative element, the more deshielded the hydrogen and the more the downfield chemical shift of that hydrogen. Let us consider these examples below. The CH3 group of the ethane is observed at the chemical shift of 0.9 ppm, but when you substitute one of the CH3 with chlorine, the chemical shift moves downfield to 1.48 ppm. Then in chloromethane, the CH3 is very close to the chlorine group and the chemical shift is observed at the position of 3.05 ppm. This effect illustrates the effect of electronegative atom on the chemical shift of proton. The closer the electronegative atom to the proton, the more the downfield effect or the more the deshielded effect. Another important point that affects the proton NMR chemical shift is the hybridization. The trend of the hybridization is the sp2 hybridized hydrogen of the aromatic proton is more downfield, followed by the sp2 hybridized of an alkane, then followed by the sp of an alkyne. Then the least that is upfield is the sp3 hybridized proton. The sp2 hybridized proton is more downfield because the induced magnetic moment generated by the pi electron aligns with the magnetic field, causing downfield chemical shift. This effect is more pronounced in aromatic hydrogen because of the presence of more pi electrons. For alkynes, the induced magnetic moment is opposite to the magnetic field, causing upfield shift. If you have a look at this diagram, you notice that the induced magnetic field of the pi bond of the alkyne is in the opposite direction of the magnetic moment. This effect causes upfield shift. That is why sp2 hybridized proton is more downfield than sp hybridized proton. For this reason, sp3 hybridized proton appear at 0.90 ppm, then the sp2 hybridized proton of an alkane, for example 18, appears at 4.60 ppm. Then the aromatic proton appear within the region of 7.27 ppm, while the hydrogen of sp of an alkyne, for example, appear at 2.35 ppm because of the reasons given above. Another factor that affects proton NMR chemical shift is the type of sp3 hybridized proton. In the type of sp3 hybridized proton, we have the primary, secondary, and the tertiary. The tertiary sp3 hybridized proton is more downfield, followed by secondary, and the primary is the least. Tertiary sp3 hybridized proton is the proton with 3 alkyl groups, while secondary sp3 hybridized proton is the proton with 2 alkyl groups, while the primary sp3 hybridized proton is the proton with 1 alkyl group. Another important factor that affects proton NMR shift is resonance. Resonance causes a downfield shift to the proton in more electrophilic carbon. Let us consider this example below. This compound is an alpha-beta unsaturated carbonyl. In this alpha-beta unsaturated carbonyl, the Hb is more downfield at the chemical shift of 7.0 ppm, while the Ha is more upfield at the chemical shift of 6.0 ppm. The Hb is more downfield because the hydrogen is attached to more electrophilic carbon. That is why it's more downfield because of resonance. Another important factor that affects proton NMR chemical shift is hydrogen bonding. Hydrogen bonding causes significant downfield shift to proton that takes part in hydrogen bonding. Let us consider these examples below. The proton of phenol appears at the chemical shift of 9.0 ppm. The proton of 2-hydroxybenzaldehyde is significantly downfield than the proton of phenol because the proton of 2-hydroxybenzaldehyde is engaged in hydrogen bonding with oxygen. That is why it appeared at the chemical shift of 15.0 ppm. Another important factor that affects proton NMR chemical shift is the conformation, especially in chair conformation. In chair conformation, we have two positions the hydrogen can assume. That two positions are the axial and the equatorial positions. The equatorial hydrogen is more downfield than the axial hydrogen. Ring size is also an important factor that affects proton chemical shift. As the ring size increases, the proton chemical shift moves upfield due to anisotropic effects and unique orbital bonding arrangement. Let us examine these examples below. As the ring size increases from cyclobutane to cyclopentane and down to cyclohexane, we observe a decrease in the chemical shift towards upfield shift from 1.96 in ppm for cyclobutane to 1.50 ppm in cyclopentane and to 1.44 in cyclohexane. Thank you for listening to my video. Please like, subscribe and share. If you have any question, do not hesitate to leave your questions in the comment section. Thank you.